Welcome, everyone. The title of the webinar today is Driving Digital Transformation in the Metals Industry, Change Management, Predictive Analytics, and Advanced Material Tracking. Before we start the webinar, I would like to go through some important reminders for all of you. Please note that the attendee audio has been disabled. Questions to the presenter should be submitted via the Q&A feature. Please avoid sending any questions in the chat box. If you send them to the chat, we will ask you to resend them to the Q&A. And this way we can keep track on all the questions. The questions will be answered after each and every presentation and also at the end of the webinar. Please note that the session is being recorded and will be available for on-demand replay on AIST's website. Photos or recordings of presentations are prohibited, and if you have any technical difficulties, please contact training@aist.org. I kindly ask you to review the AIST antitrust guidelines on this page. The antitrust guidelines emphasize the antitrust law that prohibits agreements between individuals to regulate prices and to hinder or limit a competitor. Please also review the AIST anti-harassment policy, which emphasizes the importance of providing a harassment-free environment, regardless of age, race, disability, gender, or gender identity. Upcoming training seminars here at AIST are the Industrial Automation and Control Systems Fundamentals, which will be held on 9 to 12th of March, 2026 in Indianapolis, and the Digital Transformation Forum for the Steel Industry, which will be held on 13th to 14th of October, 2026 in Pittsburgh, Pennsylvania. The forum will organize 3 panel discussions, which will focus on steel production, AI and generative AI, digitalization and safety. And currently the call for abstracts and call for panelists are open, and please submit your contributions to the website above by 15th of December. I would hereby like to thank the sponsor for the event today, Radix. Radix was founded in 2010 and is a privately held technology solutions and service company operating globally, empowering customers with consulting, engineering, operations technology, and digital solutions. Radix provides technology-based, data-driven solutions to asset-intensive industries, and their cutting-edge industrial solutions elevate business and asset performance, optimize processes, and drive technology effectively, all while integrating strategic consulting with engineering, operations technology, and software. So thank you very much for sponsoring this event. I would hereby like to introduce to you the moderator for the webinar today, Jacqueline Peintinger. Jacqueline is a product marketing manager at Ametek Surface Vision, a global leader in automated surface inspection and process monitoring solutions. And she has a background in business administration and psychology. Jacqueline has spent most of her career in the steel industry, specializing in sales and marketing for advanced digitalization and AI-driven technologies. And her professional journey includes key roles at Queen Logic and SMS Group, where she supported digital transformation initiatives for steel production, and at Smart Steel Technologies, where she helped bring cutting-edge AI solutions to industrial applications. At Ametek Surface Vision, Jacqueline now leads strategic marketing efforts that connect innovative inspection technologies with the evolving needs of global manufacturing customers. I would hereby like to give the word over to Jacqueline.
Yeah, thank you for the introduction, Alicia, and a very warm welcome from my side to everyone joining us today from around the world. We're excited to have you here for our webinar on driving digital transformation in the metals industry. Yeah, we have some great speakers and presentations lined up for you today. But before we dive into the presentations, I'd like to briefly go over again how we'll manage the Q&A sessions throughout the webinar. So please, as mentioned, submit all your questions using the Q&A feature on the bottom here. This will allow us to keep track of all your questions. And after each presentation, we'll take about 5 minutes for a couple of questions for each speaker to keep the session flowing and give each presenter enough time. And once all 3 presentations have concluded, we'll open the floor for a broader Q&A session. I have now the great pleasure to introduce to you our speakers for today, starting with Andre Ruiz-Furtado. Andre is a chemical engineer passionate about leveraging technology to enhance process performance and improve people's daily lives. With 10 years of experience, he has led projects that improved industrial performance, increased production, reduced equipment failures, and developed tools to support more effective decision-making. He applies advanced and regulatory process control towers for process monitoring, and data science to create solutions that positively impact both industry and society. Title of his presentation today is Change Management in Digital Transformation, Key Strategies for Successful Implementation. Our second presenter is Harsh Singh. He's a data scientist at Danieli USA, where he applies machine learning and predictive analytics to enhance steelmaking processes, improve product quality, and support technical sales with data-driven insights. With a background in mathematics, he has developed models for real-time anomaly detection, predictive maintenance, and process optimization in industrial production. In his upcoming presentation, Singh will discuss his work on anomaly detection in continuous casting, where he built machine learning models to identify breakouts early using sensor data. His approach helps reduce downtime and improve efficiency. Beyond quality control, he also explores predictive analytics applications to forecast equipment failures and optimize production schedules. Presentation title is Predictive Anomaly Detection in Continuous Casting, Lessons from Real-World ML Use Cases. And last but not least, David Kober. David is the Vice President of Sales and Marketing at Global Gauge Corp and serves as Vice Chair of AIST's Digitalization Applications Technology Committee. A graduate of Auburn University with a degree in mechanical engineering, David blends technical expertise with a proven track record of leading high-performing sales teams. His hands-on experience in mechatronics, industrial control systems, and robotics equips him to address operational challenges and champion advanced measurement and digitalization solutions. David is passionate about bridging the gap between data and action, helping organizations streamline operations, improve efficiency, and adopt transformative technologies in the metals and manufacturing industries. Title of his presentation, Fingerprinting Coils at the Edge, Machine Learning with X-ray Gauge Data for Smarter Material Tracking. And with no further ado, I'll hand it off to Andre.
Thanks, Jacqueline. Welcome, everyone. Let me share my screen so we can get started. All right, so today I'm going to talk about change management and digital transformation, key strategies for successful implementations. So here we have a asset performance management journey that here at Radix we have designed all of these these boxes. There are projects or programs that we designed specifically to help asset performance management, help companies achieve the maximum value of their assets. All of these projects, they usually end up being digital tools. They're going to be incorporated into day-to-day of those corporations. Since they are all tools, we usually highlight the one of this box on the very bottom, which is the daily work routine management, where since these are all tools, they're going to be used by people, right? If those people are not properly engaged, they don't have the proper training, they don't have written work instructions, or roles and responsibilities are not defined, all of these projects are going to fail. So we know that AI, machine learning, and digital tools, they're very good, that they're really accelerating the performance of many industries, but there's still tools that are going to be used by people. If those people are not actually actively engaged in using those tools, make sure those tools are actually improving and delivering value, all of those projects are going to fail. So we know that makes management of change really important and is key to the success of all of these implementations. Here we have a little description of before a digital solution, what usually happens inside the industry, right? Maybe an operator or engineer or analyst needs to understand a problem. They usually have a lot of data spread across multiple sources, and they need to understand a lot of different software to how do I get the data from my ERP system, how do I get data from my data historian, how do I get data from the production planning. They do that manually. That is time consuming. You need to know each different software. You put everything together, and then the operator or engineer needs to analyze the data and try to understand how do they make the best decision out of that problem, and then they act on the process, and then they kind of have to do all over again to understand if what they did actually had the outcome that they desired, right? But all of this cycle, this is highly dependent on whoever is running this problem analysis, knowledge and time. This is very time consuming. And for complex and dynamic process, it's hard to achieve consistent results. So what happens if we have a digital solution, right? Now, the first thing about digital solutions, we're usually going to unify all the data. And that's independent of how many different data sources we have. We're going to put everything under one place, have one source of truth with all the data. And then on top of, since the data now is already in the same place, now we can build solutions that can really accelerate the decision-making process. Now we can build dashboards that give you reports of exactly what you need to know to make the right decisions. And we can go even further, have the system analyze the problem and already tell us, all right, for this problem that you're looking at right now, these would be the optimal actions that you could take. And then a user could select one of those actions, take the action, and then the system will already tell you back if what you did is actually working or not, and keep this loop running way faster than before with all those time-consuming tasks, right? So if you have digital tools that's unifying all the data and showing you everything that you could do and making that faster, now decisions are faster and less dependent on individual expertise, and complex process become consistent and optimized and scalable. So this is a very significant change, right? So you can imagine, like, maybe for an operator, you tell him or her that now you have a digital solution that's telling him exactly what's wrong in their process and how to solve it, right? A lot of questions will come up for him, like, will this digital tool replace my role? How do I actually use this new system? Why is this system recommending this action? Why isn't the tool considering the factors that I know are important? These settings don't look right. How can I adjust them? I don't trust this approach, but management says I have to use it. But if the tool makes a mistake, will I be blamed for it? So we see that there's a lot of change going on here. And if we don't address that from the beginning, we might see a lot of resistance in using this new tool. And if the change management is not done properly right, the project will fail because people just don't trust the tool, right? We're moving from manual data analysis and time-consuming decision making to faster, more consistent data-driven decisions. Here are some examples of methodologies for or models for management of change. We have Cotter's 8-step change model, unfreeze, change, refreeze, Adhikar, McKinsey, 7S framework, and Maurer 3 levels of resistance. Today we're going to talk about the Maurer 3 levels of resistance because I think it fits right into the digital solutions. So here's the Maurer 3 levels of resistance. The first level is I don't get it. Is the easiest one. Whoever is receiving the change, whoever is part of the change, just don't understand what the solution is all about, right? The second one, I don't like it. Now the person understands the change, but doesn't agree with it. So I don't like what you're doing. So then you might see resistance due to that. The third level is the hardest one, is I don't like you. So the people, they understand the changes, they agree with it, but they just don't like whoever is implementing it. And when we say here you, doesn't necessarily mean the person leading the change, but it could be what that person represents or the group that they come from. An easy example would be maybe corporate projects don't have a good view from the site people, and then when a corporate project comes into the site too much top down, they might see some resistance of like, I don't like this project because it's a corporate project, so I'm not gonna follow along with it. All right, so how do we let's dive a little deeper here on the levels. So the first one, the signs of resistance are usually disagreement over data or rationale, lack of awareness of critical details, repeated requests for clarification, hesitation due to uncertainty, and the root causes usually are poor communication, insufficient or ineffective training, lack of clarity in objectives. This one is the easiest one, right? Because the people just don't understand what the change is all about. All you gotta do is make sure people understand, right? Go do training, Q&A sessions, make sure you have open dialogue so people actually ask questions, use data and case studies, try to approach the explanation in different ways, have multiple ways to explain. And I think the last strategy there, specific language, is very important because let's say like we're implementing predictive maintenance, you're developing machine learning models, and you have all of that language on machine learning that maybe it's not too easy to understand for someone who doesn't know machine learning, who doesn't know much about statistics at all, right? So make sure when you explain, you address your language to the public, right? Make sure you're speaking the same language of whoever is receiving. And I don't mean language, but like English, Portuguese, and Spanish, but like use the same words that the operator might use to explain your problems. Second level is I don't like it. Uh, Here where it comes usually the fear and concern for job security, like is this will replace me? Uh, you're gonna see if signs resistance withdraw from discussions or passive resistance, increased rumors or speculation about the change, hesitation to engage or adopt new process. So the people just don't like it, so they're not gonna follow along, right? So the root causes are previous negative experience with change initiatives, insufficient support systems for adaptation, unclear impact of change on individual roles, misalignment between personal values and proposed change. So here, effective strategies, I think listen and emphasize and empathize is important, and we should do that uh, pre-reactive, right? Before we even communicate the change, we should think, all right, how will people listen to this change? How will they react? And let's already come up with how can we explain that the change is good and not actually bad, right? For example, I worked a lot with advanced process controls and APCs. They really make a really complex process almost run by itself, right? Operator only has to turn the on button in the APC if the APC is properly configured, and the APC is going to take care of the process for him. The operator moves from having to actively control the process to now a more backseat operation, just make sure the APC is doing the right decisions. if you don't communicate that APC is there to help the operator, make sure that now the operator has more time to do other tasks and not have to be too much time consuming, they will assume the APC will eventually replace them. And if that happens, operator is not going to turn the APC on and your project will fail. So then other strategies generally recognize and address emotional response proactively, engage employees early in co-creating the change process. This one it's really talked about, right? Like before even actually getting your hands on the project, go to the area, to the potential users, show them the ideas, collect their ideas, and use that in creating the process and creating the project. The last level, which is the trickiest one, and it's hard, it's easier to avoid it. But after this is happening, the I don't like you is happening, it's really tricky to overcome it, but it is possible, right? So the signs of resistance are open defiance or direct opposition to change, refusal to engage in discussions or collaborate, distrust toward the person or group leading the change, formation of alliance to resist the initiative, frequent questioning of motives rather than the change itself. So the classic example here is the corporate project going into a site, right? Uh, so this usually comes from pre-existing mistrust or corporate leadership or external teams, perception of top-down enforcement without local involvements, cultural or organizational tensions between different groups. Uh, so how do we solve this, right? I said that it's easier to avoid it if you do it right in the beginning, right? Especially for like if you're a corporate person doing a local project, uh, you have to try to blend in, right? Like and do social activities, right? Before actually jumping into the meeting, into the technical details, try to get to know the persons involved in the project, have a cup of coffee, talk about yourself, try to make sure people are talking about themselves, really get to know the person, right? Develop a real relationship so you get disassociated from what you're representing, right? Like this is this it so they will see like, all right, it's Andre that's implementing this project. This is, although it's a corporate project, I trust this guy. So let's go with this guy. So if the very beginning you actually try to build relationships with the people involved, you're definitely going to avoid I don't like you. But as you go along the project and you start facing the resistance, uh, the best way to solve this is to find a champion, right? To find someone in the site that doesn't have the resistance and try to use that person in a good way, of course, to take a little bit more of the lead of who represents the project, and make sure people are following that guy or that woman, following that person. So we change the focus on, all right, this is a corporate project. No, this is a project that's being led by this person. So we have to find someone who people trust and have that person taking more of a lead, and so we can break this resistance. And now you're going to do a little exercise of how we can use this change management model in a project, right? I'll try not to take too long here, but we can look at this as a risk management problem, right? So for a predictive maintenance project, uh, people might be confused, right? They can ask, how can a system possibly know that something is going to break before it actually breaks, right? Uh, there's a maintenance planner that's been doing that for 30 years, and he's going to look at that. Oh no, I don't trust this. Like this doesn't make sense. How can a model actually know when it's going to break? I've been here for so long, I never seen anything like that. Uh, then how to mitigate those risks with simple workshops, with real plant failures, bring examples from other predictive maintenance, uh, make some hands-on role-based training, like give those people some data and try to teach them how modeling works, how machine learning works, and have them create a model and predict something so they can start trusting it, right? But then we might get to I don't like it, right? Now they understand the concept, but that they still resist it. So there's fear for job replacement, right? The planner can say, all right, I've been doing this for so long. Now this tool is doing all my job. Experienced staff may push back, saying, we've been doing this for many years with Excel. Now the key here is reframing, right? Predictive maintenance is not about replacing people, it's about supporting them. We need to emphasize the higher value tasks people can focus on when routine monitoring is automated. And by involving staff directly, including thresholds, they become part of the solution instead of feeling excluded by it. And the last one, we might fall down in the mistrust of corporate or IT, reluctant to share failure data, dismissing alarms in meetings. And how do we overcome this one? You build trust by listening first. So we have to make sure we understand how do they know if something's going to fail or not, and try to get that into the model so everyone's building everything together, celebrating small wins and engaging with the champions. Now we have some other examples here with production planning scheduling. It's really similar from predictive maintenance in a way. Now we have a program, a software that is analyzing all the data, all the mass balance of the plant, looking at a bunch of data, running a bunch of equations, and give you, all right, this is your optimal schedule, or your optimal production schedule. And all right, the planner might say, all right, I don't trust this. How do I know if it's actually considering this constraint and this relationship? So how to mitigate that? Transparent explanation of the optimization, side-by-side comparison with old schedules. We can pull historical data. All right, you did this one, right? Let me show you that the tool will calculate this schedule, and they're really similar. And then I don't like it. I think this one really goes into fear of losing control for the scheduling. And we know that sometimes scheduling has some flexibility and some decisions that are not necessarily the optimal decision. So we have to explain that the tools are going to really accelerate their job, so they have more time to think on those different scenarios, right? You're going to reduce repetitive work, and emphasize that the planner roles are the planner's role is in the exceptions, but the day-to-day thing is going to be done by the software. The last one, I don't like you. This one might be similar for all of them, right? You need to engage and build relationships. And as for soft sensors, so now how can a software know the carbon percentage without lab data, right? Can you imagine like the soft sensor saying the carbon percentage is going down, but the operator doesn't see it, still doesn't have the lab data, and then you're telling him, all right, you should act now before we get a problem. Operator says, no, let's wait for the lab data. You have to build that relationship and really explain to them how the correlations are work, similar to the predictive model, right? When they say they don't like it, maybe lab people, quality people might feel bypassed. Operator might prefer to wait for lab results. Here you have to really sit down with operators and do the day-to-day thing with them, and make sure you're testing and understanding their fears and explaining. Do all the empathy thing here. And I don't like you, again, you build relationships. And APC, this is the last example that we have. This is really interesting because sometimes APCs, they might have different strategies than the operator might be used to. So then it gets really tricky, right? You have to, again, build relationship, make sure you have open dialogue, explain what APC will do, hear what operator thinks about that, have a little technical debate, and make sure everyone gets on the same page. I don't like it. It's really important to make sure operators don't think the APC will replace them. So make sure they're moving from an active driving of the process to a more sit back operation, so they have time to look for the exceptions and the different scenarios and work on different process. And the last one, I don't like you, you build a relationship. Grab a cup of coffee, have some good conversation, talk about life, ask about family, ask about football, and you build that relationship, and that will reward you with some good allies for the project. The conclusion, digital transformation success is not only technical, even though we have a lot of technical advancement over the years, from hardware to software, AI, machine learning, There's a lot of technology going up, right? But it's still about people. If people don't trust what you're doing, if they don't like it, if they don't understand it, it's not going to work, right? Resistance naturally comes in three levels. I don't get it. I don't like it. I don't like you. Anticipating resistance early helps you plan mitigation strategies. That's what we try to show in those four examples. As you start your project, think of how the users will receive that, what will they think, and how can you anticipate their resistance and tackle it before it actually happens. In the steel projects, prediction maintenance, planning and scheduling, software and APC success depend on the clarity, explain simply, show real examples, trust, respect, local expertise, build champions, and engagement. Involve people in the journey, not just the rollout. And that's it. Thank you. If you follow the QR code, we can connect on LinkedIn and have more discussions about change management in digital projects.
Yeah, Andre, thank you so much for your presentation. That was a very valuable insight, and I couldn't agree more. Been looking at many digital projects, and it is about people at the end of the day as well. So let's open the floor for some questions. Please put them in the Q&A section below. While we are waiting for questions coming in, Andre, I have actually one. Are there specific KPIs or qualitative indicators you recommend tracking over time? You mentioned building relationships for sure. Maybe can you elaborate on that?
Yes, so I think maybe on a software side of things, it's usually nice to build a access tracking, right? If you can understand who is accessing your software, how long do they stay there, how often do they do that on a daily basis, weekly basis, and as you follow it, you actually see, all right, so we just released the software, like say like the planning and scheduling software. All right, they usually look at it 8 a.m. in the morning, then they don't open it again. And then ask question, all right, why are they not using it anymore? And then you all right, let's have some like a new workshop. Let's do with them for like a week. And then you see they're gonna access more the tool, and you keep tracking that. If the number falls down again, all right, people are not using the tool anymore. Well, what's going on? And then you design tasks to get that engagement back up. And but I think this might be a more direct uh, approach. But as you design the project, I think this is really soft skills, right? You have to get the feel of the people. When you go like present the status of how the project's working and whatnot, maybe if you feel the environment of the meeting is too technical, too tense, maybe you need to work on that, right? Like do some icebreakers before the project. Maybe try to build more open dialogue sessions and really try to understand where the resistance is and yeah, so it's a little bit more on the soft side of things. But as you have your software developed, you just track how much people are actually using it.
Thank you very much. We have one more question. What are the most common mistakes in change initiatives?
I think the common mistakes, uh, I would say, is getting too technical. I think it's forgetting the people side. And I understand that, like, especially with AI and machine learning, we're usually very excited about the technology, but that we get so excited that we forget about people, right? And I think going along with that is not changing your language to whoever the user is, right? Maybe you have like a really good data scientist, is really good at that, but maybe he doesn't have good soft skills. He's not very good at communicating his ideas outside of a data science group. And if you focus too much on the technology to communicate to the user, you might lose them, right? And you're gonna fall on the first one of I don't understand it, right? And going alongside with that is when you get too technical too soon and you don't start building the relationship, maybe in the future you're gonna even get into the I don't like you, right? You're gonna build the I don't like you because people will just see you as a technical guy who just thinks they know everything and they ignore the local expertise because he's so good at statistics and he doesn't hear our opinion. So I think that is the main mistake that I see is getting too technical too soon, ignoring other people's opinion, and that will just make the project go downhill. And it's really easy to solve that, right? You just have to have a little empathy and as I said, grabbing a cup of coffee with people and have good conversations and actually actively try to build the relationships before you get into the technical stuff.
Excellent, Andre. Thank you so much for your presentation. Let's move over to our second presentation by Harsh Singh. Harsh, take it away.
Hi everyone, just give me a moment to share my screen. Good morning everyone. Today I'm going to talk about one more use case of machine learning um, before you today. What we are going to talk about is predicting breakouts in continuous casting and how that is very relevant to the current steel industry at large. This is a small diagram which is walking through the different components and the steps involved in the continuous casting process. As you can see, the ladle is transferring uh, the molten steel into the tun dish, and then it is slowly dripping. Using the stops, like when the stopper open, it is slowly dripping, and then you got these copper plates in which are fitted inside the mold, and sometimes, most of the times, you also add some powder to maintain the consistency. And as the molten steel is rolling down, there are in many cases, there is a sudden spike in the temperature or in the pressure levels, or when the molten metal slips down, you have a lot of cooling going on through multiple sprays at multiple steps, like primary cooling, secondary cooling. You have approximately, depending on the make of the mill, you have 7 to 8 like levels of cooling. And our digital solution, what we worked on is that we installed sensor at each particular instance, like measuring the temperature. Also, we have one sensor in the tonnage, which is also measuring the consistency or like the density of the molten steel that is ideal for the process. So there are these three key reasons why I believe, and this is also an ongoing area of research for not only like companies which are working in this industry, but also there are companies like Microsoft which are thinking about entering this field, so that we can take our learnings from data in like the finance industry or in the shipping industry or wherever, like we a banking industry where we have like immense application of data, like where we have tested the models. Uh, that is there, and plus, like whenever a breakout happens, we are looking at roughly or 1 day of like at least a day of shutdown, like depending on the condition. We are incurring a lot of costs in repairs, scrap. Also, like your efficiency is going down because we are also losing on in the downtime, like we're not producing. And each minute or each hour the mill is not producing, we are losing hundreds of thousands of dollars, if not millions. And also, like beyond like just like the quantitative impact and like the money impact, it's also like a very very big safety concern, because in the breakout, the molten steel edge just blasts. And depending on the intensity of the blast, the personnel working there also come under like heavy risk. So I'm going to talk about one particular use case that I worked upon. Is we had real-time production data from a casting mill from one of our customers. So the mill, we took the operational data for 244 days of active like working time of this casting mill. And as I talked about, as you can see in the process variables, we are taking mold thermocool temperatures, cooling water flow pressure, mold oscillation parameters, like when when the mold is shaking, like that frequency is also really important. Like if that frequency is not right, the mold is not gonna flow the way it should be flowing down, and could like also lead to breakout. So this is just like a very short like timeline of like the casting process that we observed. So as you can see, like the green blocks show when the casting mill was performing normally without any breakouts, and then these red blocks that you see above is actually the downtime, or is the time where like the breakouts have occurred. So we have like time series data from like these sensors to the detail of like 10 milliseconds. Like we have immense amount of data. So I classify the data into anomaly, which is like it covers a period from the start of the casting until the breakout occurs. That's the casting period. And normal represents successful casting cycles without breakouts. It was a little a challenge to shift to the data, clean the data, make sure that we are not ignoring the like just for the sake of computation. Like since we have limited computation, or like there is immense amount of data for us to build a model, we made sure that we are taking all the active time data, so that we are not missing out on any critical part or like time data, like which will hamper our analysis. So when I did like univariate and bivariate analysis, which means when I took like one factor, let's say I took like temperature, and I'm comparing it to the pressure at that particular point, I found like the distribution of for most of the factors was uniform. As in, like if you see this graph below, you can see like more or less in the normal as well as the anomaly phase. Uh, this is this is the casting speed visual that I am showing you guys. You can see like it's following the same trend, and there is not much that we can do just by having the data there. But what we found something interesting is that if you take the same data, and like you are just visualizing the times, like the car, like you're just visualizing the casting speed, and you see like you see a sudden dip in the tundish level, and then you see slowly rising and stagnating. This we found out that was a precursor. Like whenever the mill operator is visualizing the real time signal like this, it gives like a pre-intimation that something could be wrong. This is a list of all the 26 factors that we took into our data set. We have roughly 80 to 90 sensors, but like the domain experts, they suggested based on seeing the data that these are the important factors that could help us in addressing the problem at hand. The problem being like we need to predict we need to predict the probability of breakout. So using advanced statistical methods, I developed a binary classification model to predict breakout risk in the casting process. This is a little bit of a math in up besides the formula that you read on the left. If you look on the graph on the right, you are what we are trying to do is build like a sigmoid curve, like a boundary curve, which can classify the data points, which means, for example, the data points on the right are classified as 1, the data points on the left are classified as 0. So based on this Z, that this equation, you see WTX plus V, we are building like a sigmoid function to achieve our goal. So these are the results that we got from the model building process. As you can see that we have very high recall. In plain English, that being meaning that we are able to capture approximately 94% of breakouts, but the precision is only 56%. The reason why, so in data science, we do a balance between precision and recall, because if you increase the recall, you can have a lower precision. The reason why I chose to optimize for recall is that missing a breakout is a very costly, it's a very costly mistake. So we would rather have more false negatives, more false alarms, just to make sure that we are not missing the actual breakouts, because the cost of missing breakouts is high. And we achieved a fairly accurate model despite this limitation which comes. And these are the factors, these are the weights for the factors that we got that are more important in the breakout prediction. One thing I would like to clarify is that there are two kind, if I did not clarify, what we are trying to do is we are trying to predict the instance of breakout at each data point. Another strategy that we tried testing was we took those anomaly and those normal blocks that I showed you before. We considered each of them as one sequence, and we applied like the same model to predict it. And we did not get very promising results, because we felt like the data, because the casting, the normal and the anomaly phases, they are not like they are not cyclical, or there is no pattern. So that is why we are analyzing these variables that you see to predict as to what is the magnitude of impact that the change in readings for these particular factors affect breakout. Here I'm going to talk about some limitations. Um, since we have tested our model on only one particular data set for one particular casting mill, this is still not a very general purpose model that can be implemented to any casting mill, regardless of its architecture of its or operating condition. The good news is that automation has implemented the solutions at various client mills. So we are acquiring good amount of data, and it is helping us in refining the model so that our model is more robust and has more general purpose application across the industry. Third point is reiterating what Andre spoke to us at length about, is to getting like buy-in from the mill, the operation staff, getting them to trust that the model will have some false positives is an interesting challenge, because if we come from a point and we say that we are very confident in our model and it is going to work all the time, like we might come off as that. It's very difficult to convince the operational staff that despite the fact that our model will have lesser false flags, but still getting that buy-in from the mill staff, the operational staff, is a key challenge. With that, I leave the floor open to questions, and thank you very much for attending this webinar and hearing me out.
Thank you very much, Harsh. That was a very great presentation. We do have a question for you. It is, does the model accuracy, precision, recall vary widely from mill to mill in your experience?
It's we have only tested on 2 more mills, and on the second and on both the mills, we did see a little variance. And unfortunately, I'm not a mechanical engineer by profession. I'm a mathematician. So I'm working with the engineering and the operations team to really understand, like, why am I seeing, this fluctuation, and what could be the possible reason, or if my math or my model or my code is wrong. So very great question.
Thank you. We have one more question. How the machine learning performance compared to thermocouple breakout detection system? How is the machine learning performance compared to thermocouple breakout detection?
Okay. 1 second. Yes. So the thermocouple detector sensors, they are located near. I would say. Let me pull up the diagram 1 second. Can you guys see my screen?
Yes.
Yeah. So the thermocouple sensors, they're located somewhere here. So if the frequency of the is not matching on the left and on the right side, like if there is some variance, or if the frequency is not what is defined under the mill operating condition, we are seeing that the mold is not flowing continuously and leads to a breakout when it's going down the unit.
We have a few more questions that we will tackle after the third presentation. So thank you again very much. And David, let's see what you have for us today.
Very good. Thank you very much. Hopefully you can all see my screen at this point.
Yes.
So yeah, thank you for the introduction. Good morning, good afternoon, good evening. Like was mentioned before, it sounds like we've got attendees from all over the world. So thank you again for your time. So today I'll be walking us through how we can leverage X-ray thickness gauge data combined with machine learning and various algorithms on the data sets to fingerprint coils and ensure the steel production process. So our focus today will be threefold. First, we're going to talk a little bit about the challenges of coil tracking. Then we'll talk about how non-contact measurement systems can provide the data that we need to be able to get to the third point on how machine learning transforms that data into actionable coil fingerprinting. So not just something written on the sidewall of the coil, but an inherent internal property of the coil. And so along the way, we'll highlight some practical benefits for not only production quality and efficiency, but also the safety aspect of things as well. So as everybody here on the call is well aware, steel coils move through many processes in their life cycle within a plant. So we'll go from hot rolling to pickling, cold rolling, packaging, storage, and oftentimes there's even more steps than that through the process. But at each stage, they may be stored, moved, perhaps they get relabeled, split into multiple coils. So there's a lot of different processing steps that expose risk for errors, whether it's a wrong assignment, a mislabeling, or perhaps an unreported rewind. Those can all create mix-ups that kind of ripple downstream throughout the process. So when we look at these multiple steps that a coil go through, the risk becomes very clear. Once a coil is misidentified at one stage, that that misidentification can follow it throughout the process. And even with our most advanced automated warehousing systems, there's inherent, people problems with the data entry aspect of things, and those can't prevent mismatches if the wrong identity is carried forward. And again, this is why a more inherent verification method is required. But as was talked about before, getting reliable, accurate data is really important to be able to achieve the end result here. So I want to take a couple steps back and talk about one of the strengths that we already have in this industry, and that is a plethora of data sets to pull from. In particular, we'll talk about non-contact measurement systems that, there's various different types, whether it be thickness gauges, width, coating weight, other vision-based quality systems. But we'll focus more so on the thickness gauge aspect for the purpose of this discussion, as these gives us real-time visibility without touching the steel and a detailed lengthwise thickness profile of every coil. So the idea is, can we use existing data in a smarter way, not just for process control such as AGC, but also for coil tracking and coil identity verification. So when we go to understand the data, we need to understand the equipment or the sensors that are acquiring the data directly. So when we talk about radiation-based thickness gauges, we talk first about the working mechanism, the principle where radiation is passed through a steel strip. The amount that is absorbed by the material is correlated to its thickness, and this can be used in a variety of different applications, but in our case, it's used to measure thickness. There are many different types of radiation sources. What we'll often see is an electronic-based X-ray source, so it's electronically controlling the radiation generation. We'll also often see gamma sources or radioisotope sources, where the radiation generating device is by means of an element in radioactive decay. So from a control aspect, these are often much simpler designs, but of course, dealing with an element in radioactive decay, there's a lot of safety and environmental, hurdles and paperwork to make sure that you're keeping up with and leak tests and things like that. So, but again, the nice thing about this type of technology, it is a non-contact way to get the data measurement in line in real time. And so while most of us are familiar with X-ray technology and its medical uses, where the basic principle relies upon electromagnetic radiation capable of penetrating materials, there's a lot of industrial use cases for radiation-based technology. In steel rolling mill applications, the ability to measure without contacting that material, again, is very critical. And as long as we know the metallurgical makeup of the material being measured, it's a very simple mathematical function that can be calculated in real time, used to derive that thickness. But when we get into machine learning applications, it's oftentimes very important not only to understand the physics behind how the data is being collected, so that we can better understand how to leverage the algorithms on the mathematicians and the data scientists' tasks to make sure that we're properly leveraging the data sets. So we'll kind of go into just a very brief physics breakdown here on what's actually happening inside the X-ray generation device, because that's going to give us a better understanding of the data that's being produced here. And there's a really great video Clover Learning put together here. There's a link on the slide if you want to go watch the full video. But what I'll do is I'll just kind of walk through the highlights, because it gives us an overview of this process called Bremsstrahlung radiation, and it's the process that creates the X-ray photons from the X-ray tube within the X-ray generating device. And so when we go to create these X-ray photons, there's essentially three essential requirements. We need a source of free electrons, a means of accelerating those electrons, and then a process for decelerating those electrons. And so what's actually going on inside our X-ray generation device, there's those free electrons. The free electrons are created at the cathode filament through thermionic emission. Those electrons are then accelerated through the X-ray tube by a voltage and then decelerated once they interact with the tungsten atoms in the anode target, and thus creating the X-rays. And so from an elemental level, what's essentially happening is that tungsten atom has a positively charged nucleus and negatively charged electrons. When electrons from the cathode entered the anode, they are attracted to the positive charge of the nucleus. This attraction caused the electrons to slow down or break and change direction. And this lost energy from the process is released as an X-ray photon. And so this process, called Bremsstrahlung radiation, which essentially means breaking radiation once translated from German. And as we know from physics and the law of conservation of energy, this energy cannot be created or destroyed. It can only be converted from one form to another. So as we kind of step out of the physics aspect of it, learning how the electrons then interact with the tungsten atoms, the anodes, the cathodes to create the X-ray, what does this look like actually out in the mill? So here you can see just a example of what would commonly be seen in a cold mill application, where a C-frame is housing the sensored equipment for the X-ray generation device, along with the detector sensors. And so the X-ray source is emitting the X-ray that penetrates the strip as it's rolling through the process. The detectors are positioned on the opposite side of the strip, capturing the remaining X-rays after they've been attenuated or passed through the material. And then through this, the differentiation or the difference correlates to the thickness of the strip as it's passing through. So again, non-contact, real-time measurement, and extremely high accuracy that provides us precise control over product specifications. But what we can also leverage that same data set for is accessing data at the source for coil tracking verification. So in this example case, what we'll talk about is how we can address the challenge of reliable product tracking based off of this high resolution data, not just tracking, but also backtracking itself. So here we can see, from the hot strip mill, sometimes these coils will, either sit in a warehouse or sit in a coil yard before going to the next downstream process. And the challenge is pretty clear. If you guys have, walked out, a lot of times there's external databases or external labels that maybe are hand painted on the side of the coil. Sometimes there can be issues where the databases themselves are vulnerable to error. But if we look at the coil's thickness profile, so the thickness relative to the length of the coil, that is inherent. That can't be mislabeled. It can't be lost. So that's what makes it reliable for identity tracking. And so when we take that thickness profile from the exit end of the upstream process and compare it and flip it to the entry end of the downstream process, now we're not dealing with any sort of external markers. It's individual and unique for that particular product, and it can be compared to the uniqueness of a human fingerprint. And so this patented technique was developed in the early 2000s by Mr. Onhouse, and it uniquely describes these coils by extracting these so-called feature sets. And so there's specific points along the strip length that define that these features tied to their positions that eventually go on to mathematically become a unique representation of each coil, or the so-called fingerprint itself. As we look at each profile as it compares, or as it is compared between processes, the algorithm counts how many features align with the statistical tolerance, or the so-called good matches. And the higher percentage of the good matches, the stronger probability that these coils are identical. So here you can see these so-called feature sets, and then the line being drawn just to kind of visually display where these feature sets are aligned with this hot mill process, along with the, in this case, the pickling line process. And so what we've arrived at instead is a data-driven understanding of whether or not these coils are truly alike. So this is a thickness verification method of understanding whether these coils are the same. So once we're able to extract these so-called feature sets, here's where the supervised parametric regression algorithm comes into play. So this linear regression technique is trying to match the fingerprints directly. And even though they might not line up exactly, because we may have a rerind treatment, there may be some elongation or something that occurs throughout the process, we're still able to account for and adjust for that in this algorithm. And any feature pairs that fall close or within the neighborhood of this regression line are statistically summarized and treated as to whether or not this coil is a good match. So again, the higher percentage of good matches, the higher probability that we have confidence in this coil's identity. So after looking at kind of a summary of the algorithm, what does this look like in real life? So on the left-hand side and on the right-hand side, what you can see here are two similar graphs where the x-axis is these feature sets plotted along the length of the hot strip mill, and then the y-axis is the length of the pickling line. So on the right here, it's kind of hard to see, but where the regression line was attempted to be drawn here, there's only a 14% feature pair alignment within the neighborhood of this regression line. So statistically, we understand that this is highly unlikely that these two coils are the same. But on the left here, it actually looks like the line is already being highlighted. But in fact, those are just the feature sets falling so close within the neighborhood of that regression line, where 80% of the features align with the regression model. This gives us high confidence that these are in fact the same coil. So practically, the takeaway here is, by leveraging this method, we create a probabilistic verification system instead of relying on barcodes or tags or manual entry or things written on the sidewalls of the coil, where the coil can then be tracked by its unique data signature. And then here we can see the algorithm here used for plotting that regression model. Within the software tools provided, we can validate these matching results, understand the database parameters that were output from this match, look at the two thickness length profiles that are used here, and then what's I guess more important here is validating the head and tail flip that occurs. So due to the unwind and rewind treatment, oftentimes it's difficult to compare these visually. So this portion flips and stretches so that we understand if there was any rewind treatment or elongation present, that we can visually see that yes, this coil is in fact the one we think it is, and then an output of that probabilistic statistical output letting us know that yes, this is the identity of the coil that was entered into the system and that the downstream process thinks that they're getting ready to run here. In the case of a mismatch, where in the downstream process, then incorrect coil is loaded, an automatic notification is then providing not only the notification itself, but evidence of the mismatch, along with going back through the database and identifying this true coil's identity. So fundamentally, how does this happen? Well, the X-ray gauge is producing the data set that is fed into the data collection system, where the files are then stored and transferred into the kind of edge analytic platform that is cleaning the data and processing the data set for the correlation. Once that algorithm is run, that's where this information can then be provided, either in the form of a report stored in the database system, or if in the event of that backtracking scenario where we want to go find out what coil this actually is, manually allows the user to go back and look at the data set itself. So that's kind of what is happening under the hood of the data processing lifecycle. So here's an example topology. Like I mentioned, this technique was patented close to 20 years ago now. And so throughout its maturity, it's been implemented in such a way where throughout the processing of the coil, in this particular application, you can see where each one of these kind of tracking or verification steps is put into place. And so in summary, we're leveraging a simple but powerful supervised learning model to normalize the coil fingerprints and quantify identity confidence. And it's going to adjust for process differences like elongation, offset, rewind condition, sample cuts, scrap cuts, things like that. It calculates the match percentage that translates directly into that coils tracking probability. To the previous conversation earlier, earning trust within the operators who are using it. So understanding that, hey, based off of the data set, here's the statistical percentage that we're assigning to this match. And it provides a robust alternative or an addition to not only manual or tag-based tracking systems, but our automated warehousing systems, reducing errors, increasing reliability in coil logistics, and most importantly, if a incorrect coil gets loaded up into a downstream process, that can present serious safety concerns with what might happen if the setup parameters are drastically wrong within that downstream process. So in addition to all of the operational and quality benefits that these combination of tools can provide, a clear and apparent safety benefit by understanding this is in fact the coil that you think that it is. So with that, I will wrap things up. If you have any questions about non-contact measurement systems, feel free to reach out to myself at Global Gauge Corporations. If you have any questions about the algorithms, the data collection, analysis, visualization tools, please do not hesitate to reach out to our friends at IBA. I have Eric Snyder's contact information here on the page, or reach out to me and I'd be happy to pass you along to the folks over at IBA. Thank you very much.
Great presentation, David. Thank you so much. We have one question from the audience. Is there a way for this method to work without having to unwind and rewind the coils every time?
So this method actually doesn't, I would say, require winding or unwinding the coils each and every time. It's simply taking the normal process flow of that coil and the data set that's produced, and then in the downstream process, highlighting or verifying what is happening. So there's no additional rewind, unwind process that's occurring due to this, but the data set that's collected here is just going back and verifying what the thickness gauge produced as far as the data set on the upstream process to verify that the setup information entered into the downstream process, the coil ID, all of the thickness parameters, varied gauge width, all of those fun things are in fact for the particular coil that you're setting up for. So no additional processing steps, but rather just a monitoring system for verifying that this coil is in fact the one you think it is.
Sorry about that. I have one more question for you, but I was on mute. Are you able to automatically search the inventory and identify what the actual coil was based on the fingerprint if there's a mismatch, or is that a manual process?
No, that's a great question. So the system actually has that as a built-in functionality of the mismatch identification system. So once a mismatch is identified, the data will be processed and this report will be generated and sent to whomever it's set up to be notified against. And that'll have evidence of the mismatch along with an identification from going back into the database and looking at what this true coil's identity is. So here at the top, you can see the table that provides the coil that was provided to the downstream process as the setup parameter, the coil that actually was rolled and identified as a mismatch, as well as the identity of the true coil. And then this is also available to manually interact with in the live tool here. So you can see kind of all of details if you want to drill down into all of the nitty-gritty details and the data set behind everything. But typically, this would be the kind of automated report that gets generated to go back and produce the result of that situation.
Thank you. I have more questions, and we'll start in the order of the presentations. So one more question for Andre. What happens when the system's recommendation conflicts with operator experience?
It's a great question. And it's a great one to solve, right? I think it goes back to empathy and having open dialogue, right? Your trick here is you have to convince someone that has been doing that thing for 30 years that there's a better way of doing it, right? It's not easy. There's no magical answer. But if you did that relationship thing back then, you might make it easier. But you got to get down to an open dialogue, explain, try to bring in data, examples, try to present it in many different ways, run scenarios. All right. So if the process is in this situation, and you ask, what would you do? And he would describe it, and you could show, all right, the application will show this. All right, let's see what happens if we follow those different paths. Let's see what we get. And you have to, it's open dialogue, open discussion, and you have to talk about it. It's not easy, but if you have the good relationship, it's gonna make it easier.
Thank you. And Harsh, is AI better than TCBOD system?
Yes. So for our particular use case, the mills that we are collecting data on, they are not particularly using this application. We do know of a couple of mills that are using it, and their performance is like, if you compare the performance of that mill using that process to the other mills that we are doing are not using the process, we don't see much of the difference. They are still complaining about similar kind of issues and the same frequency of breakouts. So, but since you asked this question and you certainly would know more about it, I'd love to reach out to you after this webinar and we can talk about it. Thank you.
Sounds good, David. How many coils have gone through this fingerprint method? Have any been misidentified?
Yeah, I'm not sure about the exact number. I'll lean on our friends over at IBA to see if they've got a running count from where all this is installed and located. But I can for a fact answer that yes, coils have been misidentified. And over the nearly 20 years that this system has been growing and maturing, it has been very effective at providing that verification check.
Sounds good. Okay. Everybody, do you have any more questions that can be answered in this webinar? I'm sure that all of our presenters will be available for any further questions. If you need their contact information, again, feel free to reach out to any of us, AIST directly, or also myself. We still have a little bit of time. David, I have a question.
Yeah, go ahead.
So what are the key challenges when you were planning to integrate this fingerprinting solution with legacy MES and ERP systems?
Yeah, that's always a challenge, right? Because oftentimes some of that that data entry is in the legacy systems is not even kind of automated or talking from one asset to another. There's a lot of, hey, I'm going to pass this collection of paper over, and the operator is going to have to manually enter the coil ID in the next process, which of course just is another inherent risk for misidentification. So yeah, I think that's a lot of times where this becomes even more valuable in a sense. Having a system that sits off to the side of those legacy MES or ERP systems and is providing a verification step that's based off of something that's unique to the coil. It doesn't necessarily care how old or how new your ERP MES system. It's just taking the coils data from the previous process, looking at it as it's starting to be rolled in the next process, and then understanding whether or not those two things are in fact the same piece of material.
Okay, thank you so much. Okay, let's see. If you have any more questions, now is the time. Okay. That is great. I think all the questions have been answered. And now that we've heard from all three speakers, we'll start with our closing remarks. So to everybody, thank you all for attending today's webinar. We hope you found the presentations insightful and inspiring. I did. Special thank you to our speakers and to Radix, our sponsor of today's event. And yeah, in the name of AIST, we look forward to seeing you at future AIST events. And I wish everybody a great day. Thank you so much for your presentations and participation. See you soon. Take care.
Thank you.